Hey guys, this is Mrs. Tran-Bloom. So we're gonna start with 4.4 properties of rational functions. Okay, so I just want to remind you of what a rational function is. A rational, a ratio. Okay, it's like a fraction, right? So a function is when you do a vertical line test, the vertical line can only cross the function at most one point. Okay, so a rational function by definition is in the form of r of x. Okay, so some rational function written as an x as an input, where you have a p of x, which is one polynomial, divided by q of x, which is another polynomial, where p and q are just what I said earlier, both polynomials. Polynomial function. And q can never ever be 0 because q is in the denominator. Okay, so the domain of r of x is going to be all real numbers except when q is 0. Okay, so this is what a rational function is. Let me try to focus. It looks it's a little blurry. There you go. Okay. Alright, so what I'm thinking about is this. So in an example of, if I give you r of x, it doesn't have to be r. It can be f of x, g of x equals 1 over 3 minus x. Okay? So this is a rational function. 1 is a polynomial. 3 minus x is another polynomial. So this is a rational function. You can get two polynomials dividing each other. So I'm looking for, hey, what is it that the domain can be or cannot be? So what value of x is going to make this whole thing 0? So which the domain for this particular function is going to be all real numbers except 3. Because when I put 3 in, the denominator is 0. So therefore, that's what it means. Okay, let me zoom in really quick. Okay, there you go. Alright, next, vertical and horizontal asymptotes. Here we go. I'm going to zoom in really close to the box here because it's quite tiny, especially if you don't have printed notes. It's going to make it more difficult. Okay, here we go. Let r denotes a function, which is what we had earlier, r of x. If, as x approaches, so this symbol means approaches, negative infinity, or as x approaches positive infinity, the values of r of x approaches some fixed number. Let's call it, oops, my virus screen popped up. So the values of r of x approaches some fixed number, call it L. Then the line y equals L is a horizontal asymptote of the graph R. Okay, so I'm going to go in a little bit more detail in just a second. If as x approaches some number called C, the values, okay, absolute value of r of x approaches infinity, then the line x equals C is a vertical of the graph R. The graph of R never intersects a vertical asymptote. Okay? And on the side box here, I said the graph of a function may intersect a horizontal asymptote or an oblique. Okay, and just kind of repeating of the last sentence here, but never intersect a vertical asymptote. Okay. So what the heck did this whole box right here, what does it mean, right? Okay. So here we go. If x approaches negative infinity, okay? If x approaches negative infinity, so here we go. Can you see this right here? The end behavior as x approaches negative infinity, the values of r of x, okay, I'm just going to move up really quickly, approaches L, which is some value, okay, okay. So this one says, in calculus, you're going to be using the limit, the word limit, okay. The limit as x approaches infinity, the function approaches L. That is, the points on the graph of R are getting closer to the line y equals L. And y equals L is a horizontal asymptote. Okay, so what this means is, if I have a function f of x equals, let's call it 2x divided by 2x plus 1, alright? Okay. So, if you look at this piece, x approaches negative infinity. Okay, so x approaches negative infinity. The values of Rx approaches some value called L. Okay, so, negative infinity. What is negative infinity, right? So negative infinity is we're going to go very, very small or very, very large, right? That's positive infinity. So over here, as x approaches positive infinity here. So when x gets really, 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 really small, what am I going to end up with? So let's put in negative 100 for x, okay? So if I put in negative 100 for x, would you agree that this is negative 200 on the top, and it's going to divide by a negative 199, okay? So we have a negative 200 divided by a negative 199. And as I even get bigger, right? Remember, we're going to go negative infinity. So if I get negative infinity, so negative 2000 for x, if I divide this, it's going to very, very, very close to 1, okay? And even if I go negative 2000, it's going to even be more closer to 1. So what's going to happen is we're going to take these two leading terms here. So the leading term on the top and the leading term on the bottom, okay? And when I divide them, I get 1. Okay, so that's what this end behavior right here is talking about, okay? As x approaches negative infinity, a small value, okay? A negative 1 million. What is the whole function going to be about? And whatever value that it approaches, okay, as the limit when x approaches infinity, that's the horizontal asymptote. So in shorter term, we take the leading term on the top divided by the leading term on the bottom. So when I divide that, this approaches 1. And this is what the horizontal, this is what the horizontal asymptote will be if this is a given function. Okay? Alright. So another. What happens when x approaches a positive infinity? Alright? So for the same function here, the limit of the function r of x approaches some value called L as x approaches a positive infinity. So I'm going to use the same value function really quickly. So what if I put in 2000? Okay, so 2000 times 2, that's 4000. 4000 divided by 4001. Would you agree that I'm still going to approach 1? Okay, so this is also the horizontal asymptote at 1. When x approaches negative infinity or it approaches positive infinity, and they're both approaching the same value, L. Okay, in this case, L is 1 for this particular problem. Not all the time it's going to be 1. Okay. Now, what's going to happen to my vertical asymptote? Okay, so here we're going to look at the box C and box D. As x approaches C, okay, so C is some particular value, whatever this is, okay? The values of r of x approaches some infinity. Okay, that means you can't have it. We don't know what infinity is. So the limit as x approaches C, I know it's really hard to read, r of x approaches infinity. That is, okay, that is the point on the graph of r are getting closer to the line x equals c. And x equals c is a vertical asymptote. Okay, so what is it that makes it infinity? And let's talk about what infinity is. Okay, what does it mean to approach infinity? So if I give you a function, y equals 1 over x. Okay, as you know, I can't divide by 0. So that's what your teacher's been telling you, okay? You can never divide it by 0. So right now, and why is it that we can't divide by 0? Okay, so we're going to take 1 divided by, let's just say I'm going to give you a small value, 1 over 10. Okay, 1 divided by 1/10, this is what x is, okay? Gives me 10. Would you agree? How about I want something that's smaller than 1/10? 1 over 1,000, okay, is my x. I'm going to take that and divide by 1. 1 divided by 1,000 is 1,000. So I'm going to let x be small, tiny, all right? What happens if x is really even smaller than 1 over 1,000? Like 1 over 1 million, 1 over 100 million. Then would you agree that the function is going to approach some huge value? Okay, so huge, eventually it's going to be called infinity. Okay, so would you agree that this c value here, okay, this is the c value that they're talking about as x equals to c value, is going to get smaller and smaller, smaller, closer to 0, right? So when x approaches 0, my value, okay, my y is going to get closer and closer to infinity, whatever infinity is, right? So for this one, your vertical asymptote, okay, which is x has to be 0. Okay, so aka the vertical asymptote is pretty much what the domain has to exclude. Okay, so for this one, my domain is x can never ever be 0. Therefore, the vertical asymptote is at 0. Okay, so that's how they're related, the domain and the vertical asymptote. So this last piece is very similar. As x approaches c, the values of r of x approaches positive infinity. Okay, so this is kind of another way of writing it. Okay, the limit as x approaches c, I believe this is from, if you can see that, let me zoom in really quick, that's really hard to see right here. Okay, c from the left side, okay, that means from the negative side. Okay, this is the negative side right here. Okay, so the limit as x approaches c from the negative side, then r of x approaches negative infinity. Okay, and the limit as x approaches positive c, r of x approaches positive infinity. So as you can tell, when x is approaching, okay, from the negative x, oops, you can't see that. When x is approaching from the negative c here, okay, your r of x is approaching negative infinity, which is getting very, very small, right? So when x is negative 1 over 1 millionth, then my r of x is to become negative 1 million. Okay, when x is approaching positive c, okay, then r of x approaches a positive infinity. So if we're taking back to this particular function right here, when x is 1 over 1 million, then 1 divided by 1 over 1 million is a million. Okay, so that's a positive c value. It's going to be, so whatever c is, okay, whatever x is approaching, that's what your vertical asymptote is. Okay, so in shorter terms, okay, so this is very AP calculus notations here. So in shorter term, the vertical asymptote is pretty much what the domain excludes. Okay, all right. So let's kind of read on to more of the vertical asymptotes. A rational function, r of x equals, this is how we locate, how we find it, okay, equals one polynomial divided by another polynomial. When you reduce it, so that means in the lowest term, we'll have a vertical asymptote, x equals r, if r is a real 0 of the denominator, okay? That is, if x minus r is a factor of the denominator, which is qx here, of the rational function, r of x equals p of x divided by q of x. Again, in the reduced terms, then r will have the vertical asymptote when x equals 0. I mean, sorry, x equals r. And remember, keep in mind that this is what's making the denominator 0. Okay, so this is the 0 of the denominator. Okay, oblique asymptote, which is the fun piece. Okay, so oblique asymptote is what is not a vertical, which is up and down, and it's not a horizontal, which is a left and right. Okay, so oblique asymptote is a slanted line. Okay, and we're gonna find later as we go how to find an oblique asymptote. Even though right here I have a page of how to find both the horizontal asymptote and oblique, but right now we're gonna pause on that and then explain that as we go. Okay. All right. So the first piece that I would like for you to do is, this is review. Find the domain of each. Okay, so what I would love for you to do as I zoom in so you can see a little bit better if you don't have printed notes, okay? Ooh, that is super blurry. Alright, so here it is. What I would love for you to do is pause this video really quickly and tell me what the domain of each rational function is, okay? So I just want to remind you, the domain is what the denominator cannot be, okay? So when I send these notes the next day, I would like for you to have these 3 problems completed already, okay? So again, pause the video please, and then complete this particular 3 review problems. Okay, so example 1. Find the vertical, horizontal, and or oblique asymptotes, if any. Okay, so if you have a horizontal, you're not going to have an oblique. So these two is one or the other. Okay, so first, find the vertical asymptote. The vertical asymptote is pretty much looking at the denominator. Okay, so I'm going to go VA. Okay, vertical is going this way, so you know it's going to be an x equals. If you don't have an x equals for the vertical asymptote, it's going to be marked incorrect. So please just have an x equals a vertical and a y equals for horizontal or oblique. So what you're going to do is you take your denominator, so in this case 3 plus x, you set it equals to 0. Okay, remember, according to the box earlier, it says it's finding the zeros of the denominator. So if you would just solve for this, you subtract 3 from both sides. So your VA is going to be x equals to negative 3. Okay, because when x approaches negative 3, the whole function becomes undefined. Okay. All right. So how do I know if I have a horizontal or an oblique? Okay. To have a horizontal, first, I'm gonna ask you to write every single polynomial as in descending order. Okay. So I'm gonna rewrite it. So check this out. On the numerator, notice how I have a degree of 2, and on the denominator I have a degree of 1. So on the numerator, it has a higher degree than the denominator. So this is going to be an oblique. Okay, so OA. And to find an oblique answer, I'm just going to write y equals, and then just kind of box this up for now. Just get into a good habit of writing a y equals or an x equals for VA right away. And the only way you can find the answer for this is when you do long division. Okay, so you put an x plus 3 right here. You put a 5x squared here, and as you can tell, you're missing a few terms, okay? 2 to be exact. So I'm going to go in and put fillers. So plus 0x and plus 0. Okay. So 5x squared divided by x, I'm going to end up with 5x. 5x times x is going to be positive 5x squared. Remember, you got to go in and change the sign. If it's negative, you change it positive. If it's positive, you change it negative. 5x times 3 is positive 15x. But you got to change the sign to negative. So the first 2 terms will always cancel each other out. So we're going to combine those. We have negative 15x, bring down your 0. Negative 15 divided by x is going to be minus 15. Multiply it back. Negative 15 times x is a negative 15x. Change your sign, okay, to positive. Negative 15 times 3 is a negative 45. Change the sign, okay. Combine, those 2 will cancel. So your remainder is 45. Okay. Normally, you will be asked to write the remainder here. So plus 45 over your divisor. Okay. So this is what you have when you divide. Okay. That doesn't mean this is not the oblique equation, because look at this. I mean, that's another rational function. So as x approaches infinity, okay, guess what's going to happen to your remainder? As x approaches infinity, 45 divided by 1,000,003, it's going to be very, very small, closer to 0. So your oblique, you ignore the remainder. So your oblique is really 5x minus 15. And that's how you find your oblique asymptote. All right, we'll get 2 more to go, and then we'll just call it a night or a day, depending on when you're listening to this. Okay. So next, find the vertical asymptote. Okay, so take the denominator. So I'm gonna kind of organize myself here so I don't invade the other part A. Take your denominator. Here we go. VA. Write x equals. Get used to writing it. Okay. We take your denominator. We're going to set it equals to 0. Okay. This is definitely factorable. Okay, so I'm going to give you 30 seconds to factor that out. Okay, so the two factors are x plus 4, x plus 1. Take each and set it equals to 0. So x plus 4 equals 0. X plus 1 equals to 0. You're going to solve for each x. So x equals -4 and x equals to -1. These are the two values that would make the denominator undefined. That means we have 2 vertical asymptotes. Okay, so -4 and -1. Now, am I going to have a horizontal asymptote, or am I going to have an oblique asymptote? Okay, so again, we're going to look at both polynomials. The numerator and the denominator are already in descending order. So I'm just going to check out the degree. So the degree on the top, which is x. Okay, so we have the degree on the top, which is x to the 1. So degree is 1. Degree in the bottom is 2. So right now, the degree on the top is less than the degree in the bottom. Okay, in this case, we have a horizontal asymptote. So we're going to write HA. And again, we're going to write equals. And what is the equation, right? So all you have to do is take, okay, so take one term on the top, which is x, with the highest degree, divided by one term on the bottom with the highest degree. Then I would love for you to reduce 1 over x. Well, as x approaches infinity, okay, from left or right, this approaches 0. So this is going to give me a horizontal asymptote at 0. Okay. All right. So we have one last problem, and that's it. First, we're going to find the VA. Okay, so that means what values will make the denominator 0? So VA equals x equals, and I'll box that up. I'll fill that in just a second. We take the denominator. Okay, we set it equals to 0. You can solve this 2 ways. You can factor it out, or you can move the 4 over. So we can do this way. You're going to take square root to both sides. X equals 2. Don't forget the plus or minus 2. And those are your values for your VA. You have 2 of them. Now we have to decide. Is it going to be an oblique asymptote, or is it going to be a horizontal asymptote? Okay, so I'm going to tell you this is going to be a horizontal asymptote because the degree on the top is exactly the same as the degree in the bottom. Okay, so this is going to be a horizontal asymptote, and we're going to write y equals. Okay. So similarly to problem B, we're going to write y equals, take one and only one term with the highest degree, in this case x squared, on the top, divided by one and only one term, the highest degree, on the bottom. Okay. Remember earlier when we said, hey, if x approaches a really large number, okay, what is this going to be? So, x squared divided by x squared is reduce that down to 1. So this is a horizontal asymptote at y equals to 1. Okay. And before I call it a day, or before I call it a night, I'm going to recap of how to find your vertical asymptote. Okay. So to find your vertical asymptote, you're going to take each denominator and you're going to set each denominator equals to 0. You're going to solve for that regularly. Okay, and that's how you find your vertical asymptote. These values will also be the exclusion values in your domain, and that's how they're related. Okay. Now, how do I know when I have an oblique? You have an oblique asymptote is when the degree on the top is higher than the degree on the bottom. Okay, so you only pick one term. If that's the case, then you're going to have an oblique asymptote, and when you have to do long division. And in long division, you're going to ignore the remainder because as x approaches infinity, this gets closer and closer to 0. Okay, so oblique asymptote is when the degree on the top is higher than the degree on the bottom. When do we have horizontal asymptote? We have two cases. Horizontal asymptote is when the degree on the top is less than the degree on the bottom. In that case, you're always going to have a horizontal asymptote at 0. Another case of horizontal asymptote is when you have the degree on the top that's identical to the degree on the bottom. And that's the case when you reduce them is normally whatever the leading coefficient is. Okay? And that's the end of the day. And you know what? I forgot to tell you a joke. So let's tell you a joke, all right? Okay. So what do you call a dog that cries all the time? A chihuahua! So that's my chihuahua. I actually don't have a chihuahua, but that's my topic joke for the day. Have a good night, and I'll see you guys tomorrow.